All right, hello everybody. This is a re-recording of my aromaticity video because the first one I think caught a few errors, and I just wanted to re-record it to make sure you guys get accurate information, because we are kind of flying by through a lot of this information. So what I'm about to cover for aromatic compounds and what the heck they are they don't really have a lot of content on the problem sets. Like this only probably makes up the top portion of your problem set 2. Sorry about that. Problem set 2. And does that mean it's not as important? By no means, no. Knowing what aromatic compounds are and what they do, being able to identify them are extremely important because a big part of organic chemistry too are aromatic compounds. Like in test 2, when we deal with spectroscopic data, we have a whole set of rules for identifying aromatic compounds, and we'll learn about like analysis of samples, if it's aromatic or not, and we'll be getting into a lot of reactions and mechanisms of aromatic compounds, test 1 and even test 3. So it's really important that you know what the heck they are. All right. So with that being said, I'm going to go ahead and share my screen. So you guys should be able to see my screen right here. So for aromatic compounds, I want to emphasize the importance of how stable aromatic compounds are. They are extremely stable. The fact that you have a conjugated pi system, you can make so many resonance structures. It's a really nice structure. It's extremely stable. Like the entropy value of like DNA stacking because of those intercalated aromatic rings and the nucleotides, the fact that they're stacking when they become double-stranded, it's very energetically favorable because the entropy is so high. So that's biochem thing that you'll learn later on, but nonetheless, I just want to prove my point. Aromaticity is extremely stable, and so is resonance. With that being said, let's go ahead and talk about what the heck an aromatic compound is. So the first requirement for an aromatic compound is cyclic. Pretty simple. Now, cyclic just means it has one cycle that is aromatic. So that means it could most definitely be polycyclic, like naphthalene, right? Is that cyclic? Yeah, it's still cyclic. Or if you have something like this. Here. Ooh, let's make, yeah, something like this. Is that aromatic? Yes. There's still a cyclic structure. Secondly, the third requirements are kind of hand in hand. So the second one being it is planar. Planar as in, trigonal planar, where you have a system of sp2 hybridized carbons. Okay. Third, you have a continuous pi electron system. That means you have a conjugated continuous system of pi electrons, mainly pertaining to that cycle. And the last one is it follows Huckel's rule. Ooh, I don't know where that came from. Okay, I'm having technical difficulties. Give me 1 second. Okay, this should be fine. Huckel's rule. As in, it is one of the Huckel numbers. So if you remember Huckel's rule, this is something you do have to know. It's 4n plus 2, where n is any integer, any positive integer of 0, 1, 2, 3, or 4. And what does that mean? Well, if we were to plug in those integers, let's say 0, for example, 4 times 0 is 0, plus 2, our leftover sum is 2. So you have 2, and then if that integer was 1, our sum would be 6. And we just keep adding 4 to that because the value we're changing is the n. So if we start at 2, 6, 10, 14, 18, those are our Huckel numbers. So if the number of pi electrons match a Huckel number, then it is aromatic. All right. And then pi electrons being pi electrons in a pi bond or a lone pair. Now, let's draw some orbitals on what the heck these aromatic compounds are. So let's take benzene, for example. Really easy. So benzene looks like this. Let me draw out the orbitals. And you will see later on that my orbitals aren't the neatest things on the planet, but hey, you guys can probably draw better ones. So if we have electrons in those pi systems, right? And let's say I have these bonds right here, right? And I'm highlighting what I just highlighted as in the bonds, right? So those pi electrons are currently in pi orbitals. They are in a conjugated pi system. Now, we know that benzene can resonate, right? Where that pi system can go there, here, and here, vice versa. Okay. And we can get a resonance structure that looks like this. And that, if I were to redraw that, oh, oops. Okay, you're gonna need to leave. Okay. Redraw it, it now looks like this. It's pretty simple. So the main thing I want to highlight here is you have resin structures that are going or that are changing throughout that ring structure. Not only that, but you have pi orbitals that are parallel to each other and they can form a ring structure, or I mean, a racetrack, or at least a pathway for those electrons to go around, right? So if we're looking at this physically, all right, you have electrons that are zooming around at super fast speeds. And what I like to visually imagine it, because I'm a visual learner, is when those electrons are continuously moving around that system, it forms a little bit of an electron halo. Because if you're continuously making resonance structures that are just flip-flopping between each other, and those electrons are just keep moving between those pi orbitals, well, if it just keeps moving around, well, you have a now complete flat track of just electrons just moving around in a circle, just never-ending resonance structures where it just keeps going in a circle, and that's extremely stable. And that is what the continuous pi system looks like. And that's why I kind of lump 2 and 3 together, because when you have resonance structures that are continuously pushing for that planarity, because remember, each of those carbons are sp2 hybridized, right? If they're sp2 hybridized and they form resonance structures with other sp2 hybridized electrons, well, it's going to want to stay planar because it's being pushed into planarity by the pi bond. So if that pi electron system is pushing for planarity, we'll get into that a little bit more, but just know that that's what's happening. It's continuous. An electron halo, for example, just for some visual aspect, maintaining that planarity. And that halo, or that gold standard, that aromatic donut, is super important and kind of the gold standard. So you'll see in some heterocycles that lone pairs will orient themselves so that they can be in that racetrack. Because if, for example, if one of those pi electrons were facing that way, it breaks off that entire ring. It can't form resonance structures. So it will orient itself to be aligned with the other pi orbitals. But I'm getting ahead of myself. We'll get into that later. So we defined aromatic rings. There are 2 other definitions you have to know. First is anti-aromatic and non-aromatic. And I'd be thinking, is there a difference? Yes, and it's a pretty big difference. So anti-aromatic is really simple. Excuse me. It meets every single criteria for aromatic rings except for cyclic, planar, where's sp2 carbons, continuous, pi electron system. However, 4 means it's not a Huckel number. So what does that mean? Well, whatever number you have does not fall into the 4n plus 2 equation. So let's say 4, right? Let's say you had 4 pi electrons. And you get that from, let's say, a structure of cyclobutadiene, right? Cyclobutadiene, is it cyclic? Yes. Is it planar? Yes. Those carbons are sp2 hybridized. Is it a continuous pi electron system? Yes, we can. If they're all sp2 hybridized right here, we can form resonance structure like this, where those electrons moved here. Okay, so if you now have a continuous pi system, let's look at the Huckel number, right? let's look at those pi electrons. We have 2 pi bonds, and if each pi bond has 2 pi electrons, that's 4 total pi electrons. Now, let's do it. 4n plus 2 equals, let's do our sum 4. So we do a little bit of algebra. Minus 2, all right, that's 2. N is that n has to be 1/2 in order for that to be true. And n, if you remember, has to be a positive integer. 0.5 is not an integer. It has to be 0, 1, 2, 3, or 4, your integers. So it is not one of our Huckel numbers. And you're more than welcome to just memorize the Huckel numbers: 2, 6, 10, 14, 18. All right. To give you another example of an antiaromatic ring, let's do this one. Okay. You have a cyclopropene, but it's also carbanion, right? Is it cyclic? Yes. Is it planar? Yes. You have sp2 hybridized carbons. You do have an sp3 hybridized carbon here, right? And then you have to check, is it a Huckel number? Well, look at the pi electrons. You have 2 here, and then 2 here, so that's a total of 4, right? Now, I said before that the lone pairs, it will orient itself into that conjugated pi system if it can contribute to aromaticity. However, in this case, it doesn't. So whatever it does, it can't be aromatic, because if it contributes, well, it's not a Huckel number, which is an anti-aromatic ring, which is not stable. And non-aromatic just means it doesn't meet any of the 1 requirements. So if we go back to if we go back to the definitions up here, if let's say you have a cyclic structure that does not meet this requirement, right? It's not completely planar. It's non-aromatic, or it's not cyclic at all. So like a really easy example is something like this. All right. Hexo-135 triene. Is that aromatic? No, it's not cyclic. So automatically it's not aromatic. I'm trying to think of another one. Ooh, I got one. Right? Is that aromatic? No. You have sp3 hybridized carbons right here. Those are sp3. They're not planar. They're tetrahedral. So it's going to pucker a little bit. So anti-aromatic or non-aromatic just means it doesn't meet any of the 1 requirements. Now we're thinking, why do we need to know these 3 types of aromatic compounds? Or yeah, well, we have to look at stability. I said before that aromatic compounds are the most stable, because again, if you reach one of those magic Huckel numbers, then those pi electrons are in a perfect harmony. They're living an amazing life in that like halo electron ring. It's extremely stable. Now, what's mid stability is non-aromatic. Non-aromatic. And the most unstable we have is anti-aromatic. What does this mean? It means that a structure would rather be non-aromatic than anti-aromatic. So if you have a structure that, let's say, if one of the heterocyclic lone pairs donates its electrons, then it would be a non-Huckel number. So it'd rather just stay out of it and not be a continuous conjugated system because of how unstable it would be if it was anti-aromatic. I'll show you an example. I threw it out, but I probably should not have done that. Probably should wait until we have examples. So let's try it out. Okay. So we have some compounds right here. Let's just see if they're aromatic. So first off, is it planar? I'm looking at the left one, right, by the way. Yes. Is it sp2 hybridized? Is it completely planar? No. We have sp3 hybridized carbons right here. Not what we're looking for. So automatically, no, this is not aromatic. Not aromatic. Now let's look at the one right next to it. Is that aromatic? Is it cyclic? Yes. Is it planar? Same reasons? No. Right? These are sp3 hybridized. This is not aromatic. Okay. Let's go ahead and look at some structures like this one. So we have a cyclopentadiene with an empty pi orbital. All right. So we know, all right, well, we can form some resonance structures. So if, let's say this pi bond were to go over here and had a door hinge maneuver, remember your resonance moves, that hopefully you guys know. If that moves over there, well, that positive charge is now moved over here. We just did an allylic door hinge, right? We have a resonance structure, very valid resonance structure. Can this double bond do the same? Yes, we can make another resin structure. It looks like this. Now the positive charge over there. So let's answer our questions. Is it cyclic? Yes. Is it planar sp2 hybridized? Yes. Every single carbon is sp2 hybridized. Is there a continuous pi electron system? Yes, there is. If we can continuously make those resin structures as that positive charge is being moved around. Well, in actuality, that empty p orbital is being moved around. Now, last requirement, is it a Huckel number? Wait. Is it a Huckel number? Okay, well, let's look. 2, 4. We have 4 pi electrons. 4 pi electrons, that's not a Huckel number. All right. It's not a Huckel number, so it's not aromatic. Antiaromatic. Okay. Now, an argument can be made. This is probably a Dr. Berg question, but I think that positive charge could pucker up and break the planarity, so it's non-aromatic. I might have to ask Dr. Berg about that one. Anywho, the important thing is that we know that it's not aromatic, all right? Because I think the test question that you guys will have is this, which of these compounds are aromatic? You just have to circle. You don't have to identify them. So let's look at the cyclopropene again. So look, this cyclopropene, we can door hinge maneuver, have an allylic exchange where the double bond is now there, and we have a positive charge here. All right. And again, we can do it again here. An arrow. I'll charge over here. All that stuff. We have a continuous high electron system where we can make resin structures. So now let's look. Is it cyclic? Yes. Is it sp2 hybridized and planar? Yeah, it is. Every single carbon's sp2 hybridized. Is it continuous pi system? Yes. If you look at the resin structures, it has a continuous system. Is it a Huckel number? Well, let's look at the pi electrons. We have 1 pi bond. That's it. There's 2 pi electrons. Is that a Huckel number? Yeah. If remember 4n plus 2, all right, 4n plus 2, if n being any integer, let's put in 0. 4 times 0 plus 2 equals 2. 2 is one Huckel number, so this is aromatic. Yeah, that's aromatic. Now, for the pi electrons or the hybridization, does it have to be part of the ring? Yes. So if you have something like, I don't know, let's say a benzene ring. Let's do a propyl group, right? You have a propyl group on a benzene. So that's propylbenzene. Is that aromatic? The answer would be yes. Because you might be thinking, wait, these are sp3 hybridized. How can that be aromatic? Well, the compound as a whole is mostly that phenyl group or that benzene ring, okay? That's what we're looking at. These sp3 hybridized carbons, they don't do anything with the electron system. Though they're sp3 hybridized, they're not part of that conjugated pi electron ring. It doesn't want any part of that, so it's not going to do anything. So we can safely say, yeah, this compound's aromatic, cyclic. The benzene ring, or at least the ring structure that is cyclic that we're looking at, is planar, sp2 hybridized, and we have a continuous conjugated pi system. And we obviously have 6 pi electrons. It's a Huckel number. It's benzene, so it's aromatic. Now, okay. Let's look at this one. Okay. Now we have the contrast of the one we had before, where instead of a positive charge, we have negative charge. What does that mean? We have a lone pair. All right. If we have a lone pair there, I'm just going to go ahead and write that H. Okay. Now, you might be thinking, okay, let's look. Is it cyclic? Yes. Is it sp2 hybridized planar? Not really, because if you look at this carbon, and from the looks of it, that's 4 electron groups. It's not planar sp2 hybridized, but that means it's not aromatic, right? Well, that's where it kind of gets a little weird. So let's go ahead and go through the rest of the definitions, just double check, okay? So if we, let's say, move that lone pair right here, and then that lone pair goes on that carbon, we now have something that looks like this. Okay, it's one of the moves, kind of like a little like door hinge. All right. So that's one of the resin structures. And we saw before, like you can do the same here where that double bond forms. Electrons go there. Okay, this would look something like this. You have a continuous pi electron conjugated system. Now, is it a Huckel number? Okay, let's look. We have two pi bonds and a lone pair. So we have 2, 4, and then we have the 6 from the lone pair. Is 6 a Huckel number? Yes. 6 is a Huckel number. So what the heck happens? Well, if that original top carbon is sp3 hybridized, but everything else checks out, won't it want to be aromatic? Answer is yes, it would. So let's say this highlighted carbon right here. Let's just make that this point over here. We'll keep an eye on that. So I'm going to draw the orbitals over here. Again, I know my orbitals are ugly. Let's stop talking about it. I'm going to draw these pi bonds right here. So I'm going to highlight these. Let's do this. Oops. Yeah. So what I just highlighted are these pi bonds right here, right? And just to draw it again, we have, oh God, that's really ugly. Lone pair right here, and then that hydrogen in that orbital. Okay, so this lone pair right here is facing away at an angle. It can't be planar. However, if it were to orient itself just a tiny bit at an angle and make itself perpendicular to everything else, then it can contribute. So if it were to reorient itself, it would look something like this. So now that those pi electrons are now conjugated in line and parallel with those two pi bonds. And if we were to exchange and just keep moving around, it would be not only a Huckel number, but continuous. So we would reach that gold standard of aromaticity where, well, look at that. All of our pi electrons are all aligned and they're just zooming around on that racetrack. You have a halo of electrons that form a donut. I like halo more. That halo of electrons that push the planarity. So what do I mean by this? The general rule for lone pairs, whether it be on a carbon or a heteroatom, if a lone pair can orient itself to contribute to aromaticity, it will. It's just goes to show how stable aromaticity is. It will literally orient itself and have some bond angle strain so that you can have an aromatic compound. Okay, I'm going to say it one more time. If a lone pair can orient itself to contribute to aromaticity, it will. If it can be aromatic, it will. So it'll orient itself so that it can partake in that conjugated pi system. And then now you have an aromatic halo and it's extremely stable. All right. So let's look at some heterocycles where we see that. So this first one, this is our oh so lovely pyridine. It is our non-nucleophilic base that we use in various reactions back in semester 1. It is one of the aromatic heterocycles you have to know. Pyridine has a nitrogen that takes place of a carbon in a benzene ring and has a lone pair. Okay, so what's the hybridization of that nitrogen? It's sp2 hybridized. So if it's planar and it's facing away, just doing its own thing, let's draw the orbitals and see if those electrons will want to participate in aromaticity or not. So let me draw the orbitals. Okay. Remember, nitrogen's already sp2 hybridized, so it doesn't have 4 groups, kind of like this carbon, because that carbon, if you remember, that was sp3 hybridized. So that's why it was this was making like that 109.5 degree angle. Though it would be less than ideal because it's a lone pair, but that's OChem 1 stuff. Don't worry. So let's go back to pyridine. Come on. You still have that one right there. Okay. Those pi electrons in that p orbital. So this is what it forms, right? So the 3 bonds I just highlighted right here. Okay. So let's analyze it. Is it cyclic? Yes. Is it planar sp2 hybridized? Yes. Is it continuous pi system? Yes. From the looks of it, it acts the same as benzene. You can make a bunch of resin structures, blah, 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 blah. 4, is it a Huckel number? Well, let's look at the pi bonds. We have 2, 4, 6. 6. Is 6 a Huckel number? It is. 2, 6, 10, 14, 18. 6 is the result of n being an integer of 1. 4 times 1 plus 2, that is 6. So it's already aromatic. So does the lone pair want to participate? No, because if it were to participate, you would have a pi electron system consisting of 8, and that's not a Huckel number. So that lone pair is perfectly happy just sitting on the sidelines while we have an amazing, already existing pi electron halo that's keeping that pyridine planar. All right, this lone pair just wants to face away from it. It doesn't want to participate, because if it were, it would not be a Huckel number. That goes back to the rule. If a lone pair can contribute to aromaticity, it will. So the lone pair, not pyridine, if it were to participate, it would not contribute to aromaticity because the compound's already aromatic. It's already a Huckel number. So it doesn't. Conversely, let's look at pyrrole. Pyrrole, as in like parole lobster, something like that. What was I using? Red. All right, pyrrole. Let's look at the orbitals. Okay. We have like this, electron, they'll lone pair. So let me highlight in blue this time, all right? What I just highlighted there are these 2 double bonds. Now, as it is it aromatic? Is it cyclic? Yes. Is it planar? That nitrogen's sp3 hybridized, so no. Is it a continuous pi electron system? No, because right now, as I'm describing it, the nitrogen's not doing anything. So right now, it's non-aromatic. But again, I just want to emphasize the point. If a lone pair can contribute to aromaticity, it will. So what if that lone pair were to contribute? Because right now, with the 2 pi bonds, it's a Huckel number of 4. It's an pi electron total of 4, which is not a Huckel number. So if this were to reorient itself to make something like this, I'm just going to draw the top portions. Okay. Now it's in line with those pi bonds, and it can now make a continuous resin structure cycle, right? Continuous, never-ending cycle of pi electrons. And what is that? That is our oh so amazing halo that we like so much, our aromatic halo. Our electrons are just zooming around infinitely, and it pushes the planarity. And then the lone pair that's left, well, it's just going to stay there and kind of like pyridine, just face away, right? So does a lone pair in the nitrogen pyrrole planar aromaticity? Yes, it does. Because again, a lone pair, if it can contribute to aromaticity, it will participate. It'll orient itself so that it's perfectly parallel and aligned with the other pi bonds and the pi electron system. All right, so that's it on heterocycles. Now let's go into some examples. Some of these are a little bit niche. I pulled some of them from the tests, from test prior. I've pulled some just from various notes or from office hours from last year. So this compound on the top left, this is pyrene. This is one of the aromatic compounds you do have to memorize. Pyrene is 4-ring structure. Can you stop? You're mad. Fine. Okay. Now, let's look at pyrene. Is it cyclic? Yes. Is it sp2 hybridized and planar? Yes. Right? So far, what I'm looking at is pyrene, and every single carbon is sp2 hybridized and planar. Now, Is it a continuous conjugated pi electron system? Yes, you have double bonds that are next to each other. They can just continuously like flip flop and form resonance structures. Is it a Huckel number? Well, let's look. We have, it's going to blow your mind. 2, 4, 6, 8, 10, 12, 14, 16, question mark. Right now, 2, 4, 6, 8, 10, 12, 14, 16. 16 pi electrons. Is that a Huckel number? No, but you just said that it's aromatic because it is aromatic. How the hell does that make sense? Well, this is OChem. We love throwing bullshit stuff at you. So the reason why this is aromatic is this double bond, it does not partake in the aromatic ring. Because remember, the aromatic halo just happens like on the outermost carbons on the aromatic ring. So if that middle double bond were not, let's say, didn't participate, right? You would have a nice, beautiful halo of, let's double check, 2, 4, 6, 8, 10, 12, 14. If the halo just stayed outside of that, you would have a pi electron system of 14 pi electrons, which is a Huckel number, and it keeps the planarity. So since it's on the outer portions of that ring structure, it keeps everything planar like a pancake because the halo is just squeezing everything down, making sure that it's still planar. So pyrene, is it aromatic? Yes. Does it follow Huckel's rule? Yes, because we just want to worry about the outer electrons. All right. So if you look over here, or the outer carbons, this double bond, for example, does that mean that doesn't partake in it? Well, let's look at the carbons it's connected to. It's connected to, oh shit. Pardon me. I mean, oh crap. Okay. Let's look at the carbons it's connected to. It's connected to this carbon, that carbon. Are those part of the outer rings of carbons? Yes, it is, because it forms this entire structure right here. That outer perimeter, those carbons are a part of it. So, yeah. So be aware of that. We'll get to that later, but let's go ahead and get to this one. All right. Is this compound cyclic? Yes. Is it sp2 hybridized planar? Yes. All those outer electrons, they do push for planarity, but conversely, compared to the one on the left, this middle one, that's sp3 hybridized. That's sp3 hybridized. Let's keep that in mind. Now, is it a continuous conjugated pi system? For the outer double bonds, yes. Right here, yeah, it's continuous. Let's look at the pi electrons. We have 2, 4, 6, 8, 10, 12. 12 pi electrons. Is that a Huckel number? No. So what the heck is happening? Well, I can tell you right now for a fact, it is not aromatic, because no matter what it can do, it can't move electrons anywhere from any place to force itself to be aromatic. It can't do that, no matter what. It's in a catch-22. So what the heck happens? It has 12 pi electrons, and there's an sp3 hybridized carbon in the middle. Is it aromatic, non-aromatic, or anti-aromatic? Well, which one's more stable? Remember what I said above, where a compound would rather be non-aromatic than anti-aromatic. So what does that mean? Remember, if anti-aromatic is every single quality of aromatic rings except the Huckel number, so anti-aromatic compounds are still planar because of that halo, it would rather pucker itself around that sp3 hybridized carbon and break the planarity. Because if it breaks the planarity, then it would be non-aromatic rather than anti-aromatic. Just some food for thought. If you didn't catch on to that, don't stress about it. That won't be on the test, maybe, hopefully. Yeah. Okay. I digress. That's a bird question. Might be one of the curveballs on the test, so it could be extra credit. I don't know. Now let's look at this one. Okay. Is it cyclic? Yes. Are all the carbons sp2 hybridized? Yes. 1, 2, 3, 4. Yeah, all those carbons are sp2 hybridized carbons. Is there a continuous pi electron system? Yes. That can door hinge over there, have the positive charge hypothetically be there, door hinge over, blah, blah, blah. It keeps doing that. Make sure you review on the resin structures, because I'm expecting you guys to know this. Now, if it's a conjugated pi system continuous, excuse me. Let's look at the pi electrons. We have 2, 4, 6, 8, 10. 10 pi electrons. Is that a Huckel number? Yeah, that is a Huckel number. So if it meets all the requirements, that's aromatic. Okay, now let's look at over here. Oh, non-arrow. This is aromatic. Okay, over here. Is it cyclic? Yes. Is it sp2 hybridized? For the most part, but uh-oh. Here, I'll put a star there. I guess I'll just erase it. Oops. Hey, I didn't curse this time. Okay. sp2 hybridized, or sp3 hybridized. Let's look at the pi electrons. 2, 4, 6, 8, 10, 12. Same kind of deal. This is non-aromatic. Okay. So we have 2, 4, 6, 8, 10, 12. 12 pi electrons. What would rather be non-aromatic or anti-aromatic? It would rather pucker around that sp3 hybridized carbon right here and break that plane area and be non-aromatic rather than being anti-aromatic. So hopefully you guys kind of get that. We're going to go over a few more examples on some like the last of the niche rules. Okay. So let's take a look at this one. So this compound right here, this is seen in some of your problem sets. Is this compound aromatic? Well, first off, the main thing I want to note is that oxygen with the 2 lone pairs. Right now, that breaks that continuous pi system. But let's see what it can do. So right now, if that oxygen were to stay out of it, okay, if it were to stay out of it and just keep doing its thing, and the top 3 pi electrons just keep resonating around each other, your resonance hybrid would look something like this. Okay. If that's what your resonance hybrid looks like, actually, I don't know if there'd be partial. I forgot. Let's just keep it at that. That's what your resonance hybrid looks like. Is that hybrid aromatic? Well, is it cyclic? Yes. Is it sp2 hybridized planar? Well, for that for those resonance structures, for that hybrid, where those double bonds are, for the most part, yeah. But is it continuous? No, it's not continuous. It's not aromatic. Yeah. However, if a lone pair can contribute to aromaticity, it will. So let's see if it will contribute to aromaticity. So let's say one of those lone pairs, kind of like what happened in parole, shifted itself and made itself parallel with the other pi bonds. So if it did, you can form various resonance structures that look like this. So here, resonance structures that look like this. So lone pair is here, that. And another resonance structure that looks like this. Oops. There we go. Like that. And it continuously does that. Is it continuous? Yes. So let's go back through our requirements. Is it cyclic? Yes. Is it sp2 hybridized planar? Yes. Obviously, other than that lone pair, but again, it's trying to orient itself to be parallel with those p orbitals. So yeah. Is it continuous? Yes. Is it a Huckel number? Well, if we have the 3 pi bonds, that's 6 pi electrons, and the lone pair, that's 8 pi electrons. Is that a Huckel number? No. Oh shit. Why is that? Why can't it do that? Isn't this aromatic then? Is it not aromatic? The answer is no, it's not aromatic. Because no matter what it does, it's in a catch-22. It can't be aromatic. So if the lone pair were to stay out of it, it fails to meet requirement 3, being a continuous pi electron system. If the pi electrons were to participate, it would fail requirement 4, where it has to be a Huckel number. So no matter what, it fails at one odd thing. And no matter what, it's not aromatic. So what would it rather be? Well, if you remember, the compound would rather be non-aromatic than anti-aromatic. So my bet is that lone pair would rather just stay out of it and keep itself non-aromatic rather than to contribute and become antiaromatic. Crazy, right? Yeah. We gotta love this godforsaken class. We love OChem. I want to hear you guys say it next time I see you. We love OChem. I know. Now, the next rule about aromatic compounds is you cannot have any trans alkenes. All right. So the cyclic structure you can't have any trans alkenes because, well, if they were trans, hydrogen here, hydrogen here. I'm just showing the hydrogens on the outer carbons just for some reference. Hydrogen here, because they're trans, right? Well, look at that. There's steric strain. Those hydrogens are up in each other's business. They don't want to do that. You don't want two protons that close to each other. That's not going to happen. So is that aromatic? No, it's going to want to pucker itself and break that planarity because of how unstable that is, right? Generally, you don't see trans alkenes in cyclic structures. On the other hand, what are the exceptions? Well, the only exceptions to having a trans alkenes in an aromatic compound is you need a really big ring. I would say about 16 or 18 or more. I think how much is in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 rings. You need 18 rings for that aromatic compound to allow for trans alkenes. Because let's take a look at this alkene, for example. This alkene is trans, right? So hydrogen right here, hydrogen right here. However, if you look at it, this hydrogen and that hydrogen, they're far away enough from each other. They're not up in each other's business. So is this aromatic? Yes. Oh, wait, before we do that, I'm getting ahead of myself. Is this cyclic? Yes. All right, all of these compounds, sp2 hybridized and planar? Yes. Let's look at the pi electrons. We have 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 is one of the Huckel numbers because the 4n plus 2, let's say n was, I don't know, 4. All right, if n was 4, you would have 16 plus 2 equals 18. 18 pi electrons, that is a Huckel number. So it's aromatic. Great. Awesome. Love that. That's like the last topic, Frost diagrams. And the main thing about Frost diagrams is when you have that diagram right here, whatever, one of the vertices on your polygon has to be directly below that dot in the center. All right. So if you were to have a hexagon, right? Dot was there. You need to have something like this, where one of the vertices is directly under it. If you were to have a pentagon, right? Whatever. No, we're not going to look at that. One of the vertices has to be directly under it. If you were to look at I almost said butane, a square, I know my polygons, that have to be directly under it. Okay. Just general rule. Why is that? I don't know. Go ask an advanced organic chemist in that 5,000 level class. I don't know. This is just Frost diagrams. Don't think about it. So if we were looking at the Frost diagram of benzene, right, we have a central dot, and we were to draw a hexagon where the bottom would be right below the dot. Let's draw lines at each of the vertices. Okay. Anything below the dot is a bonding orbital. So this is pi orbital 1, pi 2, pi 3. Below the dot, anything above the dot are anti-bonding. So this is pi 4 star, pi 5 star, pi 6 star. Now let's look at the pi electrons. We have 2, 4, 6 pi electrons we can assign. So 1, 2, 3, 4. Keep going. 5, 6. With 6 pi electrons, well, is this compound aromatic? Well, by definition of aromaticity, if we're using the Frost diagrams, if the bonding orbitals for the Frost diagram are completely filled, it's aromatic. Right? It's aromatic. So let's say I left that example down there. Let's do this for example. Let's bring back our anti-aromatic compound, cyclobutadiene. Okay. So that's a square. something like this. Okay. So anything above the line is antibonding. I4. Below the line is bonding. Sorry. I2. Okay. So we have 2, 4. We have 4 pi electrons. Okay. So 1, 2, 3, 4. That's it. Are those bonding orbitals completely filled? No, we don't. Or no, it's not. So this compound is not aromatic. And you might be asked on a question, like draw the frost diagram of this compound and explain why it is not aromatic. That's all you have to write. This compound is not aromatic because the bonding orbitals on the frost diagram are not completely filled. That's it. That's it. Okay, now let's look at this one. Cyclopropene again. So bring the vertices so that 1 is directly below the dot. All right, so it's pi 1, pi 2 star, pi 3 star. All right, we have 2, 4. Okay, 2, 3, 4. Uh-oh. Those 2 electrons are on anti-bonding orbitals. That can't happen. That's against the rules. That's prohibited. You can't do that. So that is, what did I just do? Whatever. That is not aromatic. Let's redraw that circle. No, not my circle. Okay. My crude circle, ignore it. Conversely, let's bring back that aromatic compound, cyclopropene, but with an empty pi orbital. Okay, let's redraw it. We have same vertices, pi bonding orbital 1, and then pi 2 and pi 3 are anti-bonding. So we only have 2 pi electrons. Well, let's look at it. 1, 2. Are all of the bonding orbitals filled? Yes, they are. Yeah. And that's kind of where I want to build the pattern, right? So I'm going to use a, let's do a bright green, right? So if it was a triangle, right, that's the smallest cyclic structure we can have. It needs 2 pi electrons. It needs 2 pi electrons in order to fill its bonding orbitals. Let's bring it up a notch. Butane, it needs 1, 2, 3, 4, 5, 6. 6 pi electrons. Oops. Yeah. If we were to look at pentane, here, let's not half-ass this. Needs 1, 2, 3, 4, 5, 6. 6 pi electrons. Hexagon, 1, 2, 3, 4, 5, 6. Needs 6 electrons to fill the bonding orbitals. Well, 2 and 6, those look like Huckel numbers. That's crazy, right? Yeah, that's pretty crazy. Yeah. So those are frost diagrams, and I'm going to stop sharing. So if you guys have any questions, reach back out to me and the other TAs. Yeah, have the good rest of your week, and hopefully you guys make use of the Quizlets.